The third speaker of this part of the event is Dr. Pengpeng Hu. We met each other at Coventry University, but now he is at the University of Manchester. He's a senior lecturer in fashion technology at the Department of Materials. And he's going to talk about cost-efficient 3D body scanning and measurement. Dr. Hu, please go ahead.
Okay, thanks for the introduction and also thanks for the invitation. So it's my pleasure to give a talk here. So I'm going to briefly introduce our recent work from our research team. So the title is the cost-effective three-dimensional body scanning and measurement. Actually, we're using AI and the low-cost device like a mobile phone and the depth camera. So I lead the research team called AI for Engineering. So currently, we are primarily working on the fashion and healthcare. So this is the team member, because I noticed that I only have 25 minutes, so I just try to skip some slides. So this figure summarized the research in our team. So from the view of the algorithm, it's called geometric deep learning. So we do the deep learning for point cloud. So point cloud is the data format. So we have the image, we have the CID model, we have the different data formats. So for us, we focus on point cloud. And I will also briefly introduce what is the definition of the point cloud. So based on this technology, we do the application for three-dimensional body scanning, body measurement, virtual garment, and the wearable technology. And we're also interested to transfer our research to the product. So we have some successful example about the technology transfer. So currently we do something like the fashion and the healthcare. So this is the abstract of today's talk. I'm going to introduce that from the 7 parts. So first, what is the point cloud? So actually, because I know that the audience here, maybe you are the experts for mathematics, so it's very easy to understand that because in image we have the pixel, and for point cloud, if we want to represent the position of one point, only one point, we can use in XYZ coordinates. Suppose that we have a lot of points, then we give a new name. We call it a point cloud. So once we have a lot of points or a set of points, we can represent different geometry like the rubbish, burning, and the donuts. So from the view of the matrix, you see that. So this is actually the matrix with size of the n times 3. So n indicates a number and 3 indicates XYZ dimension. So each row represents 1 point. So this is definition of the point. And recently, actually, the depth image has been very popularly used because previously we have the low-cost device, the RGB depth camera, and also even for your mobile phone. I think that's more than 15% of the mobile phone now in the marketing, we have the depth camera, even if you never use it. So what you need to do, just download some app and then access the depth camera. So you can capture the depth image and also convert the depth image to the point, because you have the parameters of the camera already. And point cloud has been widely used like the self-driving and other domain, remote sensing. So before we introduce that, how can we learn the feature from point cloud? So let's review that, how can we do that for image? So this is the image, and we know that image is the matrix. So each element here represents a pixel. So we have the image, and we're using the popular CNN, convolution neural networks, to extract them, and then we generate the feature. Then we integrate the feature to different probability. And here it shows that, okay, we have the high one, the car. So it means that we can predict this image of the car. But can we using the same method? So this is the operation for CNN. I guess that maybe most of you are familiar with that, and due to the time limitation, I just skip it. So for the image, so what is the difference? So the first question is that, can we directly apply the CNN to precise the point cloud? The answer is no. Why? Let's come back. So this is the image, a flower, right? And each pixel, they have the order. It's not good if you just move this pixel to another position. If we change the order like this one, we randomly change the order, you can generate nothing. So this image is not the original image like this one. So it means that image is the structured data, the order matters. However, so suppose that this is the matrix, and we know that this matrix represents the point cloud because each row represents one position for point. And this is the n times 3, each row represents 1 point. So suppose that we move the order, so the first point to the second one, what happened? Actually, from the view of the geometry, nothing happened because this point represents the position. So once you change the order of the element of the point, the position didn't change unless you do the rotation or translation operation. But here, if you just simply change the order, so nothing changed, it means that the point cloud itself is actually unordered or unstructured data. So it means that CNN cannot be directly applied to precise the point cloud. So how can we do that? So in 2017, so people invented the technology called PointNet. So actually, the idea is similar to CNN, but we didn't using the convolution. We're using the fully connected layer or MLP. So we have the shell MLP. The shell here means that we have the same architecture and the same weight, the learning weight. And we do the processing for one point because we have a three-dimensional x, y, z, and we can convert the x, y, z coordinate to a new vector. And we do this again for the second point. Then we generate another vector for the another feature vector for this point. And we just iteratively do this for all the points. Then we can convert the n times 3 matrix to another one, n times 1024. So the 1024 here is actually the size of the vector. So vector means feature. So each feature indicates only one point. However, we know that for deep learning, for training neural networks, so we cannot have such a large scale data size because here the dimension increased from 3 to 1024. So the training can be a burden because due to the GPU storage. And what we can do, we're using the pooling operation, for example, the max pooling. So for each column, if you select the maximum number, you just have one, and you can compress the high dimension data into the low dimension data. So similar here, so we have the n times 1024 data matrix. And if we focus on the first column and we only select the maximum, so we can compress this matrix to a vector 1024. So in this way, such vector we call global feature. So this is the feature represents we learn from the point cloud. So once we have the feature, we can do it. We can interpret the feature into different domain. It's up to your application. For example, we can do it for classification, segmentation, or even reconstruction. So this is just the basic explanation. How can we do the feature learning from point cloud? And because my work usually focuses on the human body, so sometimes we also need to generate the larger scale data size. But unlike other data size, so to capture the human data is very time consuming and it's very expensive. So we have to rely on some parametric model. So here we're using the very popular one called simple model. So this is the model generates the human body, and we have two parameters. So one is called beta, one is called theta. So beta indicates the shape, and theta indicates the pose. So like the video demonstrates, once we change the shape parameters, you see that we can generate different body shape. And if we change the pose parameters, you can change the posture. So we know that a human, we only have two factors, human body and human pose. So once we can generate different human body shapes and we can generate different body shapes, body postures, then we can generate a lot of data size like this one. So when we fix the pose, the same posture, we can have different body size. When we fix the same body shape, we can have different posture. In this way, we can generate the data size. Okay, so next, I'm going to provide the details about our work. So why do we need body measurement and body scanning? Because this is very useful. For example, when we do online shopping, if you didn't know your body size, you buy some clothing online, and once you receive it, you have to return it because it's not fit your body. And besides, we also need the body measurement to do the medical application. For example, obesity study and measurement of newborns. Also for the disabled person to design the prosthetics. So actually, body shape and body measurement is very, very important and widely used in different domains, even for the human factor application. So what is the research challenge? So currently, this is example of body scanner. Maybe some of you have experimented this already. You see that this is very, very complicated device because you have to using the whole lab to host the device, and the people stand on the platform. And you need another professional guy to do the operation. So this is a limitation. Additionally, you may notice that the people here have to take off all the clothes because currently the three-dimensional body scanning is highly reliant on the computer vision technology. So they can only capture the outermost surface. So that's why if you want to have the accurate body shape, you have to take off the clothes. But do you want to do something like this? I don't think so. Because for myself, I don't want to be almost naked in public area. So this is very important to preserve the concern to limit the usage of the three-dimensional body scanning. And additionally, you have to keep the apples because people can stand up to avoid the occlusion. So for disabled person, for example, the wheelchair user or the newborns, the old people, how can you do this? So this is challenge. And additionally, we also need measurement technology for hand, but some people, they cannot open the hand like this posture. And we also need to measure the baby, but baby, you know that the skin and bone, they are too soft. So we cannot have the very good way to contact the body. So we have to non-contact the technology to do the measurement for baby. That's why we want to do this. So try to address this problem. We do quite a lot of work in the past 5 years, and they can summarize by the three different domains. The first one is the body shape estimation and clothing. Second one, the smart body management. And the last one, how can we develop the low-cost body scanner? Because we want using the cheap way. This one is too expensive. Sometimes they may take around 300,000 pounds. So we have some papers, and this is the select way. If you are interested, you can search the Google Scholar and to read them for more details. So next, I'm going to provide the technology information, but due to the time limitation, I know that I only have 10 minutes left. So I just try to provide the idea and also the results for the methodology part. Maybe some of them I will skip them. So the first one is the body shape estimation. As I just mentioned, people have to take off the clothing like this one. Nobody like it because I don't like it. I don't believe that someone like to be naked in the public area. So our idea is that, okay, we take on the clothes and then we're using the AI, we're using the algorithm to predict the naked body. Previous methods, I mean, that's before the popular study of the AI methods. So people using the template fitting. So we have the just scan and we have the body mesh. It can be treated as the template. You have to manually select some landmark. You see that we have a dot here. And the landmark should be put very accurate. Otherwise, the template fitting is very, very bad. So this is very time consuming and highly depends on the experience of the operation. And more important, we have to predict the gap because for garment, we have the gap between the garment layer and the human skin layer. How can we predict it? So such method is not good because we lack of the physical information. So using AI methods, we can do this. How can we do that? These figures summarize the idea. So we have the just scan, and if we can using AI model, neural networks to predict the offsite. So the offsite is the vector, and then we can use the inputs to minus vector. We can generate the geometry of the naked body. So this is the idea. To implement this, we propose the architecture. So we have just the scan, and then we're using the network to learn the offsite. We're using the scan to minus the offsite, generate the initial body, but this is very rough. And then we propose the refinement module to find the results, generates the final output. So here the input is the just the human body point cloud, discrete data, and here we have the continuous repetition. We have the mesh, so the output is mesh. And to generate the data size, because we need the data size to training, we can using the capture data, but that is really expensive. For example, in Manchester, we have to spend 15 pounds to scan one person. But now I need 100,000, so that is impossible. And we also can rely on the close simulation, but unfortunately, the close simulation is very, very time consuming, and it's also expensive. For example, to design such garment, maybe the experiment tailor, they need 5 or 10 hours generate this one. But here, again, we need 100,000. So to address this problem, we proposed algorithm. So we're first using the software to generate clothing similar to this one. We're using such software. We may spend 5 hours or 10 hours, but keep in mind, we only do this one time. So once we post the garment on one template, we can transfer the garment from the template to different body and also different body shape. And such process is only half second. So this is very quick. And we have the multi-layer garment. You see that 1, 2, 3 layers here. And we also have shoes. So we can transfer the garment together with the shoes to the new body in 0.5 seconds. So this is really quick. So once we do the garment dressing, we can also propose the virtual scanner because we need to scan their data site. So we convert the mesh to the point cloud. In this way, we have the input, we have ground truth, then we can do the training. So this is the demo about our data site we proposed about 6 years ago, because this work was proposed 6 years ago. So this is the body shape. We proposed the 100,000 female and 100,000 male bodies. We also prepare 3 different clothing style. And recently, we do something more. So this year, we proposed a new and better data site. You see that we also conclude the textile information. We also include the different garment style. And this is the new data site we propose. So this video demonstrates the result. You see that the left one is the real-world data. Even our model is purely training on the synthetic design. But you can see that the result can be really good. It proves that our method can be generalized via to unseen real-world designs. Even the real-world designs consist of some noising on the crotch or the arm, but the right one, our result looks really perfect. And we also developed some software to measure. So currently, together with our industry partner, we can scan the body, wearing clothing, and then we estimate the naked body. We do the measurement. So this is very fantastic. So this result demonstrates that the overlapping between the garments, the purple one is the garment layer, and the yellow one is the skin of the human body. You see that almost the body was aligned inside the garment. It means that our method achieved the best performance. So previously, I introduced that how can we estimate body shape on clothing. However, you see that we still need the complete body. But I mentioned at home, how can we do that? You need a very expensive professional device to do this. So we think of that, is that possible? We can use the mobile phone to do the accurate, because we care about the size. We need the size should be very, very accurate. So is that possible for us using the mobile phone to reconstruct your home body shape at home? The answer is yes. So the basic idea is that we can use the mobile phone to take the 2 partial scan. So one is from the front view, one is from the back view. So once we have the 2 partial scan, if we can align them together, generate complete body shape, then this can be done. However, this is not easy. Why? Because in the past 30 years, so the previous method to do the restoration is called ICP, or the ICP-based variant. So the basic idea is that, for example, the red curve here represents source, the blue curve here represents target. So the restoration means that you need to align them together, generate such results. So they have to highly rely on the assumption that you need correspondence. So once you have points on the source, you need to find the corresponding point on the target. Then you can minimize the distance to implement the restoration. But let's come back. Our data types, we have the capture data from front view and back view. Unfortunately, we have a zero. We have a zero overlapping. So we have to say that's ICP field because we don't have such correspondence. So how can we address this problem? So if we don't have any overlap, then we propose the virtual correspondence. So this idea was built on another technology called shape completion. Shape completion means that if you have a partial scan, if you have the partial signal, you can predict the global signal. So you have partial scan, you can generate complete body shape. It means that this is the shape completion. So what our idea is that we take the 2 partial scan, and if we can predict 2 global shape and represent by the same model. So same model was introduced at the beginning. This is the parametric model. They have 1-to-1 correspondence, indicates the different color here. And once we have correspondence, we can, using ICP, to align them. We can generate the rotation and the translation. And once we have the rotation and translation, we can apply them back to the input. Then we can do the restoration for the 2 partial scan, generate the final results. So this is the idea. So the basic implication is that we train the shape completion networks twice. So the shape completion is that you have the partial scan, you have the ground truth, you have the complete body shape. And we have 2 partial scan, front view and back view. So we do the training separately twice. So once for the front view, we have the global shape. Once from the back view, we have global shape. But however, we ignore the fact that the 2 partial scan, they are captured from the same subject. So it means that the complete body shape, this one and this one, they should be same. But unfortunately, because the training was done separately, they are not really the same. So to improve the performance, we do the edit. So we do the exchange. For example, the feature here, learn from the front view, we add it to the prediction for the back view. And also for the future of the back view, we also add it to the prediction of the front view. And additionally, we also provides the transformation, so rotation and translation ground truths during training. So we rotate the front view ground truths and then align them together. In this way, we can overlap the line front view ground truths to the back view ground truths. Then we can minimize the distance to improve the virtual correspondence accuracy. And this is result. So this is real world data size captured by the connector version 1 sensors. So this is the input, blue one and red one, and you can see that we generate complete body shape. We generate complete body shape. More results can be seen here. So the top one is the partial scan. The bottom one is the globe shape. As you see here, we even have some data missing in the captured data, but it doesn't matter. Our methods still work very well to predict the restoration. So using such technology, you can do the reconstruction at home. What you need to do, just take the two partial scan. But however, as you may notice that the posture of the front view and the back view, they should be the same. So if I keep the same posture, who captures the data for me? So it means that if you stand at home and keep the pose still, you still need another person to capture the data for you. So this is not good. We hope that you can do everything by yourself. So we improve the algorithm, and you see that we allow two partial scan, but in different posture. And then we also estimate body shape on the clothing. What you need to do is just to put your camera there, and you can self-capture yourself. Then you select the front view and back view, you can generate results. So this is the algorithm. We have the integrate the beta. So we introduced that at the beginning. So the beta indicates the shape parameters because the two partial scan capture from the same subject. So the body shape should be the same, even they have different posture. So we try to recognize the beta parameters, and then we can generate results. So this is more results demonstrates the algorithm. So next, we also propose the algorithm for body measurement. For example, we have the complete scan, we have the partial scan, and we predefine measurement lines on the template. Then we train neural networks to deform the template to fit the different inputs. And finally, we transfer for the measurement lines after deformation. Similarly, we also do the measurement for hand and foot. And also, when we do the study for obesity, right, we need to measure the volume. So we also propose the algorithm, take the single scan, and we generate different body parts. We also calculate the volume from the different body parts. So this is the demonstration. How can we do the measurement?
Using only a low-cost depth sensor. The subject steps into the
scanning
area
here,
for both
we have one
front and
camera,
back scans.
and the person
Capture
standing in front of the
point
camera
clouds from each side.
perform the posture.
These point
It
clouds
can be
are
different.
raw,
What we
unregistered,
do is that
collected
we
from a
capture
dressed
two partial
person
scan,
in arbitrary poses.
and then
These
we do the
two
measurement.
raw,
We have the
partial point
deformation,
clouds then serve as inputs to measure
and
output,
we have the
which
measurement
outputs
lines there.
unclothed
Then we can
human
do the
body.
measurement. And this video demonstrates that the dynamic. You see that our hand. Sorry. Oh, it doesn't work. Why? Oh, you see that it works. So we move the hand, and you see that we can dynamically measure the size of the hand. So this is the dynamic measurement. Okay, sorry, due to the time limitation, I'm going to do that quick. And this work is to normalize posture because the initial scan posture can be different. But if you have very bad posture, it's very difficult to do the measurement or the PCA analysis. So what we do is that we propose the algorithm to do this, and just simply demonstrates the result. You see here, so we have different scan data in different posture. Even the posture is very complicated. So our algorithm can transfer the posture to the standard T-pose. And more importantly, we didn't change the body size. So the size should be the same after deformation. And also we preserve the identity. So if this is my face after deformation, after post-normalization, this is also my face. We also have some work for virtual try-on. So we give algorithm to transfer the garment to different body in different posture. Additionally, this is a very general method because unlike the previous method focused on the garment transfer, we also possible to transfer the available items. For example, the hair, the eyeglasses, the watch, the necklace, the hat, and the shoes. So we also do the animation for garments. We're using the scanning to generate the multi-layer garment. This is also a challenge. If you are interested, you can refer to the work. And this is for mannequin. I'm going to skip this one. So recently, we are primarily focused on the smart garment because in my opinion, I think that computer vision meets a very challenged by the large scale language model. Because, for example, ChatGPT can do some very computer vision task very well. So what I'm going to do is that integrate computer vision technology, also the wearable technology. We have the background of textile and the smart garments. For example, if we propose the intelligent textiles and we can predict we can detect the pressure, and from the pressure map, we can predict the posture and human body shape from the different signal. Additionally, recently, we also worked together with the doctor in King's. Is that King's? I think that's, I forgot the name, sorry. But that is a hospital in London. So we proposed the algorithm to develop the smart garment to monitor the heart failure. Finally, we are interested to the technology transfer. This is the example. So one of our algorithm to estimate body shape has been integrated product, and we helped the company generate the more than 4 million euro investment from Decathlon. And this is our product. We have the body scanner. And if you visit Belgium or France, you may experience our product. We also have the collaboration with the industry partner called Spanish for the prosthetics design. Okay, so that's all. Thank you. Sorry for the time limitation. I guess that I just exceeded some time.
And that's fine. Thank you for the presentation, Dr. Hu. If anyone has a question, we still have 3 minutes before the next presentation. Okay, Ahsan, you can ask question.
Yes, thank you, Pengpeng. Wonderful work. I just have a quick question. How willing people prefer to use this technology, like in an actual clothing shop? Are people willing to use this technology, or do you see some sort of an hesitation there?
Well, from the communication by our from our industry partner, I think that it's very easy to choose this one, because if you go to for example, myself, if I go to the clothes shop, I don't really want to try on the clothes by myself, because maybe I'm a man, because I don't like this way. I think that this is boring, and sometimes I feel a bit shy. So if they can provide the software, you just download the app, and you take the image of your body, then you can do the body measurement. So this is the easy way. And from the feedback from the company, I think that's a lot of the customers, they want to use the technology. It's not a challenge.
Okay, so there are several things in the chat I'm going to read for you. Asma Zahuri is saying, very interesting work. How does your approach handle morphological diversity across different body types while still keeping it cost effective?
Oh, this is a good question. So that's why I provide some slides to focus on how can we prepare the training design. So actually, our current training design is very large scale. We have like 300,000 body shapes. We have different, and we're also using the motion capture technology, because motion capture technology can capture the realistic human body motion. Similarly, we're also using the Frank motion. Frank motion is the technology that you can capture the body motion and also body shape. So the body shape here is represented by the parameter model, simple model. So we can use the Frank motion to capture the theta and beta parameters. Then I remember that we collect more than 2,000 different body shapes, and then another 2,000 different motion. So we just randomly combine them. So one motion, one posture, you generate a new body. One motion, one posture. This is random. In this way, our currently body shapes, we have the diversity for more than 2,000 different body shapes. It's not really accurate. I mean that currently our accuracy for the measurement is around 2 centimeters. But this is good for the everyday life clothing already. But for like the high end, the customization, like the suit, we still need the further research.
Okay, actually, next comment from Treso is mentioning shoes. So Treso is saying, best regards, Pengpeng. How good is the technology to calculate tricky details like shoe size?
Shoe size. Oh, to be honest, we didn't really test in the shoe size, because our industry partner, they focus on the human body. But this is a good question, because I also think that maybe we can collaborate with some like a professor in sport, because for sportsmen, they care about the geometry of the foot. Maybe we will do testing in the future, but right now we didn't have any number. We don't have any experience without to tell you is that the method good or not to deal with the shoes part. I'm sorry for this, but I'll keep this in mind because we indeed have such plan to validate this.
Okay, thank you, Dr. Hu.